we're both on camera. It's probably a good idea to mention that these microphones, when we're recording, are going to be live. So if you mention cookies or any other thing in the audience while the speaker is talking, we'll be able to hear it on camera. So please limit the chatter that you have and discussions you have while the speaking is going on, because other people will be able to hear it. So it's my great pleasure to introduce Dr. Dmitry Kalashnikov, which is probably the coolest name ever, without a doubt. He is an associate adjunct professor of computer science at UCI and received his PhD from Purdue University. He's also graduated from Moscow State University in Russia, graduating summa cum laude. And his work is all concerned with, he's published in several high-ranking database journals like VLDB and these various other things. And his work is concerned with entity resolution and data cleaning. And it's going to be I hope I got that right. And this is going to be very interesting, and looking forward to hearing your presentation.
All right, thank you so much for the introduction. Thank you for coming to my talk. Today I'm going to, the talk will consist of two parts. First, I will give you like a very brief and high-level overview of Project Sherlock that we have at UCI, and then I will kind of explain one particular research direction that we have. All right, so high-level introduction about Sherlock. So here is the talk overview. Basically, I'll just cover some background, and I will present to you what I call a roadmap for Project Sherlock, just to give you an idea of what we kind of working on, or we have been working on. All right, so as information integration people in this audience, you probably know this is like a typical data processing flow that you frequently see. So you have like data, which is used for analysis. On top, using the results of this analysis, you're kind of making decisions. So data could be of different types, including textual, semi-structured, multimodal, and analysis also could be of different types. So consequently, quality of data determines quality of analysis and determines the quality of decisions. And information quality was estimated to be 1 billion market by the first research group in 2008. And it's actually quite old research area. It's at least 50-year-old research area. Just to give you some quick background, so we have as an example, so we have a professor called Chen Li at UCI. He's a very nice guy. So he's a database professor, and this was his homepage. So let's kind of ask a simple real-world query. Find me in Google Scholar the paper account of UCI's Chen Li who is in CS area, right? So it's a simple question, but it's easy to answer this question. So this is a picture of an interface to a program called Publish or Perish. I don't know if you guys have seen it. So it's like, it used to be an old interface on top of Google Scholar, which allowed you to kind of compute citation counts of people. Back in the day, Google Scholar would not allow you to kind of build profiles of people. So that was the interface. So the way to query it, you would specify C. Li in this case. So you specify Chen Li, you would miss some publications. So you specify some areas of interest. And what happens, this interface returns to you that Chen Li has like 1,000 publications and citation count is like sky high. So basically what happened here, right? So what H index is also very high. So what happened here is, of course, there are like duplicate papers in Google Scholar. Also, there are duplicate authors. It's not we queried for Chen Li, but like there are many Chen Lis, right? And you would think, okay, can I still somehow kind of, answer this question? Maybe there is like a out-of-the-box solution which is maybe easy. Can I go maybe to his like homepage and just see his publications? Then I will be able to answer it. But actually, I kind of that was a trick question, because we have, for example, another Chen Li who's a student at our department, and maybe my question was about that Chen Li, right? How do we know? So what's the lesson here? The lesson here is what is known as garbage in, garbage out in the data quality. So analysis of bad data can lead to incorrect results, and you need to fix errors or account for errors before before you do any kinds of analysis. And here you have like the famous 80%, so many people will kind of refer to this 80%. So more than 80% of data mining researchers spend more than 40% of their project time on cleaning and preparation of data. So when data quality issues arise, or why, is because like of manual entering of data and making mistakes during manual entering. There are inherent data problems, so you have text and you have like a reference in this example to, you go to text and you have like J Smith, and then you have like John Smith or Jane Smith, so you don't know like is J Smith John or Jane. It's the same for basically organizations. And very frequent cases like when you see anti-resolution data quality issues is automated generation of database content, where you have lots of raw data and you're trying to create kind of a single warehouse out of it. And there has been a tremendous increase in interest in anti-resolution because of big data and because of lots of information actually collected from the internet. So what is anti-resolution? This is the definition. So it's a common data quality challenge. Its goal is to find which references co-refer or refer to the same real-world object. And people sometimes distinguish two kinds of anti-resolution. One is called lookup, and one is called grouping. So what is lookup is in the lookup you're given a clean list of objects, and your task is it's like a canonical representation of all objects that are possible in your data set. And your task is to for each reference in your data set to pinpoint the correct object. So what is grouping? So grouping is you are not given any list of objects. You just have lots of different references. And for each pair of reference, you just need to say co-refer, don't co-refer. So that's the grouping challenge. So the lookup basically corresponds to the classification challenge, and grouping corresponds to clustering challenge. So this is what we call the standard approach to entity resolution. So the way the approach would work, it would collect, so if you have like a tuple in a database, and these are, let's say, attributes of this tuple. So let's say this is a tuple Chen Li. He used to be a student at Stanford. This is his old email address. This is Chen's advisor, PhD advisor. So this is the new tuple for Chen Li, right? So he's a professor at UCI. This is his new email. And maybe this is like collaborators, and this is like collaborator Hector Garcia. So the way traditional approaches would work, they would compare basically attributes, and based on comparison of attributes, they would try to make decision match, not match. So this approach works well for many domains, but sometimes it doesn't work as well for tough cases or for certain domains. So this is an example where it doesn't work, because if you just start comparing attributes here, you see it's like student, professor, Stanford, UCI. So there is the only match you see here is here. So in the standard approach, the similarity function would be what we call feature-based similarity. But like if you want to it's still possible to link these two people to determine that these two tuples actually co-refer through various additional kind of inferences, or by analyzing additional source of information. So for example, you can see, okay, there's actually a connection through Stanford, which you might infer from some other sources. So now if you have this additional information, you might this gives you more knowledge, and you have more knowledge to tell if two people are the same or different. So modern approaches nowadays, they're not necessarily limited to feature-based comparisons. So they use all kinds of external data, such as ontologies, encyclopedias, the web. So you can ask a person to provide feedback. So you can leverage various public data sets. And you could use what we call anti-relationship graph. So, and we contributed to this area specifically, significantly. So the idea here is that, as database people, we know, or from the database sources, that many data sets are actually relational, meaning that they consist of entities. They kind of represent entities and relationships among entities. So you can visualize the data set or view the data set as an entity relationship graph, where each kind of node would represent an entity, and each edge would represent a relationship. So now you can say, in a way, it's like a simplistic view. It's like a social network in a way. So now to decide, like, if you have U and V in this graph, so you can use not only the attributes of U and V, you can also see how it's like connected in the graph. Yeah, so we contributed a lot to this area, as I said. So this is our project SHERLOCK@UCI. So it started in 2003. So it's resulted, of course, in many research publications, or in several research publications and prototype systems built. So initial motivation of our project was quality. So we were trying to basically reach, we were trying to figure out which kind of additional data sources we could use to improve the quality of entity resolution. We were not so much concerned about the efficiency, but the truth is, like, in the background we always try to kind of devise very efficient techniques, but that was not the focus. So the current motivation of our project is, of course, data, and efficiency is also a major focus. Okay, so these are the publications that we have. So these are kind of key people of Project Sherlock. The top row, students, PhD students already graduated. So the second row, it's our PhD student that are still kind of at UCI. The bottom row is like myself and Sharat, who are kind of working on this project as well. Okay, so this is the roadmap of Project Sherlock. So it kind of explains different sub areas that we looked into. So one of the big sub areas is using this entity relationship graph for as additional evidence to improve the quality of entity resolution. And so we work on both lookup and the grouping, and we applied it to a bunch of different problems. So the classic entity resolution problem, and also to the problem of web people search. So web people search is the problem where, let's say you type somebody's name, let's say in Google, it's some search engine. So what would happen, it would return to you a bunch of web pages that kind of correspond to namesakes of the person you typed, right? So if you type John Smith, you will get web pages of different John Smiths, right? So your task is to cluster web pages such that each cluster kind of corresponds to a single person. So that's web people search. So as an additional data source, we also use the web querying approach. So in web querying approach, what you can do is like, let's say again, so you have a bunch of web pages. Let's say you're trying to do web people search. So what you can do is, let's say you look at two web pages. You can extract, let's say, name entities of it, such as people, organizations, and then you could use these name entities to form queries to the web and get kind of counts how many kind of pages are returned. Not the pages themselves, but the counts of web pages. So you could leverage these statistics to improve the quality of entity resolution. Also, we looked at the problem of what we call video and image entity resolution. So it's so what we've noticed is that, like, in that domain, you have a you have a problem of person identification, where let's take Google Picasa, all right? So you have a face detection challenge where you apply Google Picasa, it will show you, okay, this guy is the same as this guy, and this guy is the same as this guy. So what we said, okay, can we, and typically, so it will say, okay, these photos are all of your photos, and this is your mom, essentially, right? But what happens if you look at Picasa, very frequently it generates clean clusters. So it would get, like, each cluster will be one person, but the clusters are split. And why they are split? Because, like, let's say maybe in one cluster person is like facing this way, and another cluster person is facing that way. So it's kind of, and the classic approach to kind of do this disambiguation of faces is using image features. So if you use image features alone, it's difficult to disambiguate. So what we said is like instead of, now it's very similar to a traditional approach. You just use like just shallow features. The question was, can you use context or different types of context and combine all these kind of features together to improve the quality? So that was one of our solutions, and we actually got a, I guess, best paper award for the framework we developed in ICMR conference. So we also looked in the human in the loop solution, so using human as additional source of information. The question here is like, all right, so you cannot ask too many questions. So which questions do you ask of humans? Another direction was querying on anti-resolution data. So in anti-resolution, what happens is like two situations can happen. You can either ask your technique to commit to a certain answer. So for example, you have a reference, it's a reference to, it says J. Smith. So you have a John Smith and you have a Jane Smith, right? So you can ask this technique, or typically you would ask this technique, well, choose one, commit to one, all right? But sometimes you don't have to do it, and sometimes you can keep the probabilistic representation. So you can say, okay, right now I know it's like 70% is Jane and 30% is John. So you can keep this probabilistic representation, and you can get higher quality of answers if you just keep stuff in the probabilistic database. So essentially, how do you, then the question becomes, how do you optimally answer like probabilistic queries on top of this representation? So, and today I'm going to talk about the third direction, which is like anti-resolution for big data. And in reality, there are two sub-directions that we have in this area. One is progressive anti-resolution, and another one is query-driven anti-resolution. So yeah, so next I'm going to talk about the query-driven anti-resolution. Do you have any questions so far? Let's switch to a different presentation. So this talk is basically our paper published in VLDB 2013. So I'm not going to reintroduce the problem of anti-resolution again. I'll just, okay, so here you have like a bunch of Ronaldos and you have UCI, and you need to kind of disambiguate. You need to say, well, this Ronaldo is this Ronaldo, and like UCI is at the University of California, Irvine, or Union Cyclist International. All right. So anti-resolution has become a niche market. There are many companies working on focusing on anti-resolution. For example, Joe Hellerstein has a trifactor, just a new approach to anti-resolution. So here are the typical anti-resolution phases, slightly simplified. So you have a bunch of references. You need to do disambiguation. So typically what would you do is, like if you have n references, for each pair of reference you need to say, corefer does not corefer. So it's a quadratic operation if you don't do anything kind of smart. So what people would do for efficiency first, they would apply blocking. So what is the blocking? They would try to partition the data set using very fast techniques, basically linear on big O of n, such that if you look at each bucket, references in each bucket might corefer, but references across buckets cannot corefer. And so that's the definition of a blocking function. So sometimes people use not one, but multiple blocking functions. So then you have like a similarity computation phase where you would compute similarity. Let's say if you have a reference R1, R6, you would compute how similar two references, maybe using features or maybe using some other information. And then you, based on these similarities, you would do clustering.
By co-referring, you mean referring to each other or both referring to?
Referring to the same objects. So you say you have one reference, it says J. Smith. You have another reference, it says Jane Smith. So you need to say, are they talking about the same person or not? Any other questions? Okay. All right, so big picture of the solution. So this is a typical ETL process. So if you have multiple data sources and you want to do some analysis of it, you would do what is called ETL, extract, transform, and load. So you extract information of your data sources, transform and clean them, and you load them into your data warehouse. So then you can do all kinds of analysis on top of this data warehouse. Again, quality of data thus determines the quality of decisions. So, so what is the query-driven approach? Query-driven approach is actually is a slightly different paradigm. It doesn't do this. What it proposes is that the user would use a query-driven interface, which would query kind of directly on these sources, and it would extract data based on query and do only minimal necessary cleaning. So it does not clean the warehouse. And the reason is that like this cleaning operation of a warehouse is could be very computationally expensive, and it's not necessarily in many situations. Yeah. So what are these situations is like big data, then you have a query on online data like meta search technology. In certain applications, you know what to clean only during query time. And also there are cases where you have like a small organization in a possession very large data set, but this organization needs to analyze a very small portion of this data. So like if it has very limited resources, there's no need to kind of clean the entire huge data set. Okay. So here is a trivial example, which is like very trivial. So if you have a query like this, select star from Scholar, so Scholar is Google Scholar. Let's say you have like a database of bibliographic entries where venue equals VLDB. So you don't need to clean the entire data set, you just can focus on VLDB publications and clean them. But this, of course, is a trivial example, right? Let's look at a more interesting example. So in this table, again, it's bibliographic entries, let's say from Google Scholar. So you have titles, like first paper towards efficiency and towards efficient entry resolution. Then you have cited attribute, right? So it says this paper is cited 65 times, venue will be, author and year, right? So in this example, papers 2, 3, 4 are actually duplicates. So they should be merged together. And papers 5, 6 are also duplicates. They should be merged together. So the ground truth is like this. So you actually have only 3 publications. So this actually happens in Google Scholar. So sometimes people refer to publications differently or slightly incorrectly. So what happened, Google Scholar would split your publication. So you would see a portion of it in one place, a portion of it in another place, and the citations should be added basically. So typically, problems like this are visualized using graphs. So this is one way to visualize it, which we use in our paper. So you have nodes for different tuples, essentially for different references to papers, and you have an edge, which signifies that 2 papers could be the same. I need to check. In this graph, this is just for our kind of for clariness. We kind of put 65 to signify that this paper has 65 citations, and this is the ground truth, which is unknown to us. So this is a separate cluster, this is a separate cluster, and this is a separate cluster. Okay. So now, if we execute the following query on top of this dirty relationship, so what we get is we'll get the first paper, which is correct. All right, and then so we need to get the second paper. So so what is the kind of standard solution? How typical approaches would kind of answer this query? The first step they would do, they would to duplicate the dirty relationship fully. How would they do it? Okay, the standard approach would call resolve functions on pairs of records. So it will call resolve on pair 1, pair 2, paper 1, paper 3, and so forth. And eventually it will get something like this. This is a clean relation. So now, once we have the clean relation, we can execute the query on top of it and get the answer. But the problem with this solution is twofold. So first of all, the number of calls to resolve can be high. It's going to be quadratic on the block size. So if you have a block of size n, it's going to be quadratic, up to quadratic. And the resolve functions, if you want to get high quality, can be expensive functions. So what is a resolve function? It's a pairwise function. It's applied to, let's say, two tuples, Ri and Rj, and it basically outputs decisions like must merge, must separate, and it could be uncertain. It says, I don't know, basically. All right. So if your resolve function says, well, I think these two records are the same, you can apply the merge function. The merge function will try to come up with a merge representation of two tuples. So it will apply combine function to combine each attribute. And there could be different merge functions and they're domain dependent. So for example, if you have something like Google Scholar, which splits papers, let's say, again, you have paper 1, paper 2, it's in reality the same, but it's kind of split because people refer to papers separately. So in Google Scholar, you would want to use something like add semantics. So meaning that if you have a paper like this, a paper like that, and in Google Scholar you see 25 and 20, it means like Google Scholar did not figure out they're the same. You need to adopt citations. But I mean, different situations it could be different. So you don't necessarily need to use add semantics. In certain domains, you need to use max or min semantics. And for categorical attributes, people typically use two semantics. One is called union semantics, so is where you keep everything. So if you're trying to merge two tuples 2 and 3, they would just keep all representations of authors. So in this case, they would keep John S. or John Smith. Or you can use like exemplar semantics, where you pick just some representation according to some rules. 1. All right. Is it clear so far?
I have a question for the motivation of doing it after the query. So is it the case that only the data is too big that you cannot do it initially, or based on the query you can do it higher, do the cleaning with a higher accuracy?
No. Yeah. So this technique is not about quality. So this technique is about the efficiency. So what happens if you have, like, let's say, a big data scenario, and you have a query with a very selective predicate, or you have a bunch of queries with very selective predicates. So you don't need to clean the entire data set. You can kind of answer your queries correctly just by doing a very small amount of cleaning. So you'll get tremendous amount of savings.
So if
that's
there are some queries that are repeating a lot, you can do the pre-processing for those queries.
So that's a kind of an interesting question, because it implies a different architecture that is considered in this paper. So you can envision as like there could be a middleware architecture where the system sits in the middle and caches the results and kind of does some smart processing. So in this situation, in this paper, it's like just an initial solution. So it basically what it does, it says, okay, I don't have this middleware architecture yet. I just query from scratch. Okay. All right. So the question now, okay, how can you use the query semantics to improve the quality of cleaning? Not to improve the quality, the efficiency of cleaning. So this is an example. So let's say you have so the query is select from R where cited the attribute is above 30. Assume we're using additive semantics. So we have a publication with citation count 65. So we know it's going to be in the answer no matter what. So if I It could be that it should be kind of, it could be that some other papers is kind of co-refer to one, but it doesn't matter because we're already including 65 in the answer. It's already above 30. It will not get out of the answer. So we can include paper 65 in the answer. And consequently, we actually don't need to call resolves like from paper 1 to paper 6, 5, 4, 3, and 2. So we can save on these resolves. Next, let's pretend our framework queries for the age between 2 and 3, which is like 25 and 20. So, and our function will return to us must merge. So now we have a combined representation for the merged papers, and the combined citation count is 45. So now we have the answer 1 and 2 merge 3. So let's pretend we're now calling a resolve on 5 and 4. All right, and again, the same logic applies to 2 and 3. We actually don't need to call resolves on edges from like on these edges, because we know this paper is already in the answer, and if it's merged with something else, it will stay in the answer. So let's pretend we call the resolve on 5 and 4. Okay.
Sorry for a question. Why is it that you're using the citation count as a criteria for joining? I mean, or not? I mean, I don't understand what the logic behind that.
So, like what we've done, we are actually parsing the query. So we have a predicate that says, I am interested, give me all papers from our relationship relation where attribute sati is above 30.
I see.
Okay.
I don't understand the difference between paper 1 and 2, 2.3, because they're going to be in the result in the same way. And if they are two papers, they will be one paper. They will be presented twice in the result.
Yeah. So that's So you will see there could be that's an excellent point. You will see there could be different answer semantics. So if you know, let's say SQL. So if you have a selection query, by default SQL uses so-called back semantics, meaning that it can return to you duplicates. So I will address it in the next slide. So it's an excellent point. So, and depending on the query semantics that you want, you can output some answers fast, but they could contain duplicates. That's exactly correct. Or you can spend more computation time and remove those duplicates. So I will explain it later.
Okay, but then the cutting criteria wouldn't be the same for the first situation or 2?
It would be, in our solution, it would be the same. The way our solution just going ahead, the way it works is basically generates a so-called representative answer, where I just want, like, the example of this query. So why would you want to use this query? Let's say you have some guy, some person in mind, and you're trying to deduplicate his publications, like Hector Garcia Molina. And you say, okay, I'm just interested in good papers of Hector Garcia Molina very quickly. So give me this list as soon as you can. So this query would output you this list, just to give you the idea, okay, these are kind of good publications of Hector. They're all good, but yeah. So, but yeah, this list can contain duplicates. Is that okay?
So I suppose you're going to talk about this next, but the way you're presenting this, you're still calling the kind of resolve function for repair, which is being very efficient. So at the end of the day, what are you going to do? Some kind of blocking, and you're only going to prune within a block? Or
Yes,
how does that
so
work? Otherwise, I mean, even if you can call R and say, well, I mean, P2 and P3, they are 45, so it's more than 30, so I have to consider them. P4 and P5 is 25, so less than 30, I'll have to consider them. But even just creating the pair, creating all pairs, quadratic, and will be too expensive. So how you going? So this is where you're going. That's very good. Let's just wait for the next slide.
Yeah. So the way it works is that I guess the key assumption here, and it's you will see it's basically a collaborated assumption you will see from the experiments, is that the bottleneck of this approach is calling resolve functions. So the resolve functions are the most expensive part of this operation. And the way the approach works is that it first applies blocking. So you have a huge data set, it would chunk it into blocks, and it would construct this graph like this. And in reality, I'm not covering it in this presentation. It constructs it very aggressively. It's not constructing stuff it doesn't need. It won't need. Yes, but in general it is quadratic, but the cost is not in constructing this graph. The cost is in calling resolve functions, which are expensive functions, or could be expensive functions, which kind of analyze stuff. It could be like, as I described in our case, even calls to the web. They could include analyzing ontologies, so they could be complex. So in general, this framework is meant for the case where resolve function is not cheap, which is frequently.
If the result function was fast, and you had a million records, just trying to do a million square is just way too many. So that's why you have to do some blocking to start with.
Yeah, that's correct. So what will happen is, like, let's say you have a data set of billion records. When you apply blocking, it could be that one block contains a million records. In this case, kind of all techniques will be slow, right? So what we are saying is it will be faster. So of course, yes. So this assumes that we are looking at a block. We are not looking at the entire data set. Okay, this is I should have said it. This is one block only. We are looking at one block.
So you're not calling resolve between 1 and 2 and 3?
I'm not calling.
In this case, because they are both in the answer, right?
Yes.
Yeah.
So yeah, because as I mentioned, there could be actually next slide explains different answer semantics. So if
though that they are indeed the co-referring, so you always get them the same answer. So if you resolve them now, you can remember that forever.
You resolve this now. There could be some optimizations. I'm just describing our solution that kind of, and we are showing that like this solution works very well. Essentially, it works better than the approaches that exist right now. But in general, you are correct. Yes. So yeah. So what we've done here to continue is like we call resolve on 5, 4, and 5, and it says must separate. So at this stage, we know these three nodes, they cannot be the same. So consequently, the only possibility is this can be the same or this can be the same. But the combined citation count is less than 30, so we don't need to call any results, any more results. Okay, so query-driven solution, we just use two results to resolve the entire kind of TOA example. So the standard transitivity closure algorithm would use something like 11 calls to resolves. So we save 9 calls to resolves. And the correlation clustering algorithm will actually call resolves on all the pairs. So it's going to take 15 resolves. So savings could be significant.
Sorry again.
Okay.
How did you choose the 2 pairs? Because you chose the correct ones to begin with.
In this algorithm, actually I will explain the algorithm later on. So there was a certain, so what we've done is like, first if I go back. All right, so what I've done first is say, okay, which nodes basically are already in the answer without resolving. And I know 65 is, right? The next thing is just say, okay, let me call on 2 and 3 because I use some policy. In reality, I can explain what policy we use. A good policy to use would be to pick edges whose combined citation count is the highest. All right, so in this case, I pick 25 plus 20 is going to be the highest, and I call the basically result on this edge.
So the policy is based on the semantics of the...
The policy is based on the semantics. Yes, that's correct. And you can imagine, well, yeah, let me, I will explain different policies later on. So this was just yeah, illustration that you could save. I'm not explaining the algorithm yet. Okay, so there could be different answer semantics. So there can be exact answer semantics, distinct answer semantics, and representative answer semantics. And if you want to basically, so the top ones are more strict, but the bottom ones are kind of more efficient. So what is the exact answer semantics? The exact answer semantics is that you are saying, I want the answer as if like I applied the cleaning techniques first, and then I ran the query. I want exactly the same answer. So that's the exact semantics. Yeah, so you need to merge 2, 3, 4 and represent this in the answer. All right, so what is the distinct answer semantics? So distinct answer semantics is that I want each cluster. So let's say let's pretend I apply some cleaning techniques fully and get the clean data set. So what I want now, I want each cluster be represented in my answer somehow by some clusters, but I don't really care about the representation. But I don't want to see duplication. So you added, you basically said, I want to, let's see an example. So the return answer would be 1 and 2. So the query was select distinct star from R where cited above 25. So paper, let's say 65 qualifies. The second paper above or equal 25. So you can output 1 and 2, and this is correct under the distinct answer semantics. Or you could return an answer like 1 and 3 and 4 merged together. So that would be distinct answer semantics. So what is the representative answer semantics? In representative answer semantics, you remove the condition that you want to see things distinct in your answer. So it's equivalent to if you have like select query in databases. So select queries can return to you duplicates unless you're using distinct, right? So here you just say, well, I want some representation of each cluster, and I don't really care if it's duplicate or not duplicate. So you can return the answer like 1, 2, 3, 4. So like for this query again, the correct answer is like you need to output cluster 1, cluster basically that corresponds to cluster 2. But if you output 1, 2, 3, and 4, so essentially you have a duplication. 2 and 3 and 4, they're kind of part of the same cluster, but you're kind of you're representing the correct clusters. You are not representing 3. So this answer is correct under the representative answer semantics.
So in that question, would you go with the count? Would be the sum of 3 and 4. So you would give like 2 with cited at 25, and then 3 and 4 with also 35. That's what you.
Yeah. Yeah. 2. So 1 will be with the count 65. 2 will be with the count 25. 3 and 4 will be count with 35. Because 20. So we are assuming additive semantics here. So 20 plus 15 is going to be 35.
Sorry, so what's the threshold to consider it exact?
The threshold?
I mean, yeah, there is at one point that, you say, okay, give me duplicates, and try to avoid them as much as possible. And the other is do not give me duplicates because I consider them an error. I assume that's the difference between the select and select exact. So what's the threshold?
So you mean like how the user decides which one to use, or?
How do you make the distinction?
So essentially, like in databases, you also have like 2 versions of select, right? So you have a select distinct and you have just select. So select distinct, what it does is kind of sorts the tuples, and then it kind of does this merging, so it eliminates duplicates. Or you can say, well, without distinct, it does not guarantee you that it will return. It will not have duplicates, and it's up to the user who's using the select query to kind of choose which is the correct version to use for her application. So because maybe it's okay to have duplicates in the answer, but get them very fast because sorting is like n log n.
Yeah, but maybe I did not understand the example. In the first case, you're going to give me 4 tuples, and you're going to merge 3 and 4. You're going to represent 3 and 4 together, but not 2, 3, and 4 together, right? And in the second example, you're going to put 2, 3, and 4 together. So why did you decide to merge 3 and 4 in the other case?
Why did
What's
they?
the threshold? Maybe I'm not getting
25 in the query.
Yeah, so essentially, if you, I guess what I'm saying is like, if you have an answer like this, 1, 2, 3, and 4, if you somehow magically came up with this answer, so this answer is correct under the representative answer semantics. So I'm just said, like, I'm not, so in this example, I'm just defining what is correct, what is incorrect. I'm not saying I'm applying a specific algorithm. I'm just giving examples of answer semantics. Is that? All right, so what is the problem? So the problem can be formulated as follows. So given a query, you need to minimize the number of resolves subject to query satisfaction. So each cluster that you can return your algorithm should satisfy the query, and it should satisfy the user-defined equivalence. The answer generated by QA for query Q should be exactly distinctly representatively equivalent to that of algorithm A. So this is a simplification of the algorithm. So first it creates graph, and as I mentioned, it actually does it very aggressively. It does not create stuff it doesn't need. It does not create some nodes and edges it doesn't need. So then it has this loop, repeat until all edges are resolved or vestigial, and I will explain to you what it means. So first it uses some edge picking policy to pick certain edges, and if those edges are not vestigial, it will call, vestigial means redundant, it will call resolve function on it. So what is this vestigiality? So vestigiality testing does the following. So it looks at a pair of, let's say, tuples, and it just outputs the answer, vestigial or not vestigial. It means that is the call to resolve is going to be redundant or not redundant for this pair. And it does this by analyzing the semantics of the query. It analyzes specifics of the combine operation. It analyzes the answer semantics and the decisions made so far by the algorithm. So what is the definition? So if regardless of the ground truth, the algorithm guarantees that by treating a certain edge as a no edge, as if it's the answer to it is no, it can still compute the correct final answer. This edge is called vestigial. Okay. So, so factors which affect vestigiality are represented as a triple. P is a predicate. This plus is a combined function, and AL is an attribute. So you can look at this predicate and classify it into three groups: in-preserving, out-preserving, and neither. So we need this classification because we want to develop algorithms that are very generic. So you can have like combination of predicates. We don't want to develop algorithms that are very specific to different predicates. So an example of an in-preserving tuple. So you have a triple like this. Let's say citations above 45. You have added semantics on cited attribute. So is it in-preserving or not? So let's say again. So in this example, you have a paper with citation 65, and so if you use additive semantics, 65 plus 25 is 90. So if it's already in the answer, it's already above 45. It will stay in the answer no matter what. If it's merged with other tuples, it will still stay in the answer. Is this clear? Okay, so this tuple is in preserving. This triple is in preserving. So what is out preserving? So let's say you have a triple like this, less or equal than 45, additive semantics and cited. So this triple is out preserving, meaning that once some entity is out of answer, it will stay out of answer. So why is it so? It's like once a paper basically you know that like, well, it's already does not satisfy 45, it will keep not satisfying the answer, because by merging you can only increase the cited count. So that's the idea. So an example of neither is equality. So give me all papers, so triple give me all papers with citation 45, additive semantics, and cited attribute. So you have like example like this. So you have a paper with cited values 25 and 20. If you use additive semantics, 25 plus 20 is 45, so it's in. And then if you merge it with another one, so it becomes 60. 45 plus 15, 60, so it's out. So it's neither in preserving and or out preserving. So how do you kind of handle queries with multiple predicates? So you can actually prove that if a combined function is in preserving, so you can prove the following properties. Based on base combined functions, combinations can be proven to be either in-preserving or out-preserving. So for example, if you have a in-preserving combined function and in-preserving combined function, then let's say and and or is also in-preserving. So how do you test for vestigiality? First, we need to we will use the notion of a click. So a click is a complete graph, of course. So this is an example. It's a complete graph. So all nodes are connected. So this is not a click. So obvious observation: if a group of nodes is not a click, then nodes in this group correspond to at least two distinct entities. So then we define the notions of a relevant click and a minimum click. So what is a relevant click? If you find in your graph a click that can change your answer, your current answer, by either like adding a new entity or deleting an entity from the current answer, so this is called a relevant click. So a relevant click is called a minimal click if no subset of its nodes form a relevant click.
Sorry, I'm getting a bit lost. So what are the edges here? So how do you determine these edges? Did you run? So why 1 and 2? Because you're considering merging just two entities, or do you actually run something to see that they're related?
Yeah. So in this example, so you applied blocking, and you construct for each block you construct this graph, and you run your algorithm. That kind of I presented an overview of this algorithm. So the way it works, it uses an edge picking strategy. So first construct this graph for each block.
So the graph for a block is fully connected.
It's yes, it's fully connected.
Everything in the block you don't know if it's
reality, it's not so in the paper, in simplistic version, you're correct. It's fully connected. In practice, if you like in the paper, maybe I can show you offline. There is an aggressive policy. You will not construct the entire graph for a block. So in general, it is quadratic initially. So then, what you do next? The graph construction is not the bottleneck. The bottleneck is calling result functions. So now,
I understand that. No, I understand. You were saying that these two situations can happen, so I just don't understand. Maybe I need to understand that part of the block that doesn't make sense for me.
Yeah.
The block will consider
so this kind of
connected, but the thing is that there's some other technique.
this kind of shows you things in the middle. Let's pretend you actually were using your algorithm, and let's say this is just the beginning. Let's say the beginning you have a fully connected graph, or maybe it's a part of this just illustrates a click. So maybe it was a block. The block contained millions of
If you control 3, I just don't understand why.
So if you
let's
say a block consists initially of just 3 papers, so you initially constructed this. So maybe your algorithm, for whatever reason, later on called resolve on 1-3, and resolve said must separate. So essentially you remove the edge.
So you're calling this sequentially, and you already
Within about 5.
So let me So you can find a relevant click. A relevant click means this click can change the answer. A minimal click says it's a relevant click, and no subset of nodes is a relevant click. So it's minimal. Yeah. So then you can prove the following theorems. Edge is vestigial if it does not belong to any of relevant clicks. So meaning that you can treat this edge as no. And second theorem is when a triple is in-preserving, so it's an optimization. An edge is vestigial if it does not belong to any of the minimal clicks. All right. So now you can do vestigiality testing using this theorem. So assume a query like this. Select from R where cited 45. So recall that this triple is in-preserving. So we can choose some edge. Let's say we choose 1-6. So it doesn't matter like if we call resolve on 1-6 or not. 65 is going to be still in the answer. It's in-preserving, so we don't need to call resolve on this edge. And actually, we don't need to call resolve on 1-5, 1-4, 1-3, 1-2 under representative semantics. So these edges are vestigial. All right. So let's say we choose edge 4 and 5. So is it vestigial or not? It's basically not vestigial because there is a click like for 2. So if all of them are yeses, then this tuple will kind of be in the answer. So essentially it's not vestigial and you need to call a result. So like yeah, I need to finish. Let me try to I guess summarize the results quickly. Maybe just show you the experimental results. Yeah. Let me quickly. So, but testing for vestigiality is NP hard. So how do you kind of do it in terms of efficiency? What you can do is you can devise inexact check whether edge can potentially be part of a click. So there is a fast algorithm. All right. So the next question is like, what's your edge picking strategy? And there could be multiple strategies. But the trick here is that this function, picking an edge, called many times, so this function itself should be very, very fast. You cannot afford to spend too much time kind of thinking which edge to pick. And what worked the best for us is that you pick the edge with the maximum weight, and the weight is computed basically as you have an attribute like cited, you just add up incident weights of incident nodes, and it forms the weight of an edge. But the idea here is that, like you in general want to quickly discover entities that can change your answer, or you want to quickly break relevant minimal clicks.
What's the initial weight?
The initial weight is like so if you have like let's say let me give an example. All right, so if you have let's say an edge, and let's say cited count is going to be let's say 65 and 10, the weight is going to be 75. It's just 65 plus 10. So this policy works the best because it's very fast and it achieves these two goals that I just mentioned. So these are our experimental results. So they are on bibliographic entries of Google Scholar for 50 researchers. So our PhD students have done tests on the larger data set, but it's not included in our paper. So we use resolve function, these two resolve functions to deduplicate, and we use very simple blocking techniques, which kind of puts the same papers, two papers in the same block if they match either on first two characters of titles or last two characters of titles. So these are the results. So here what we do is that, so this is the query, select star from R where cited above threshold, so we vary this threshold, and this is the running time of the query. So this is a transitive closure approach, which is kind of the standard solution, and this is a QDA approach. As you can see, it is faster, and this is very similar plot. Instead of plotting running time, we're plotting the average number of results. So the idea here is that you see these two plots mimic each other. Why? Because basically these two plots show that resolve is the bottleneck of anti-resolution in this case. And so what happens here is that initially everything is in the answer. So the QDA is very fast. For threshold 1, so all nodes qualify, so it can output answer very quickly. For thresholds value like 128, you see lots of potential clicks, lots of clicks kind of qualifying, so you need to do lots of work. So you see the spike. And as you increase the value of the threshold, it's kind of the running time decreases again because very few clicks are qualifying. So you can get the answer very quickly. So yeah, I guess I need to finish. So this plot plots you different query semantics. So the top line. So again, we vary the threshold value. This is again running time, number of results. So now, in addition to just applying this logic, we also need to disambiguate the results. So if we get some results back by QDA, we need to say if we want to get distinct results, we will kind of need to call resolves on the results themselves to see if they're kind of the same or different. So this adds the cost. And for different query semantics, as you can see, the cost increases, but as query becomes very selective, we still see some gains. So yeah, so we applied this technique for different types of queries. Greater, I mean, so GT is greater or equal, LT is less or equal, equality, range, categorical, and for all selection queries we see, so this is speed up for different query types, for different threshold values. So we see improvement across the board. Okay. Yeah. Yeah, but basically now ongoing work. So selection queries are not the only queries in SQL. SQL has also joins, it has aggregation, and so this is our ongoing work. So I am not going to explain joins, but we are kind of working on joins, so the paper is almost done. Yeah, so these are joins. Yeah, just to summarize the future work. So yeah, so we want to develop QDA for joins and aggregation, and we also would want to put QDA in the context. We want to integrate QDA with real systems like Google Fusion Tables, Microsoft Power Query for Excel, and integrate with the real DBMS systems system like Postgres. Okay.
Maybe time for one question only. Anyone want to have a burning desire to ask a question?
Since you mentioned edge choosing strategy, really matters in terms of how efficient you can get. So, can you describe, have you tried other strategies and how much they differ?
Yeah, so just to give you an extreme example, an obvious, what would be an obvious, if you ignore the execution time, you just say, I just want to minimize the number of resolves. Let's pretend resolves are kind of extremely kind of costly. So what would be an obvious edge picking strategy in this approach? An obvious edge picking strategy would be to say, okay, I have an edge, let me see the number of clicks or relevant clicks it is involved in. This is going to be my weight. The edge that is involved in the most relevant clicks is the most influential one, because if so what happens in anti-resolution, very frequently you have a case where you see a block and duplication is not much, right? It means that if you poke an edge, you say, tell me resolve, it will say no. These two are different. So if you see an edge that is involved in the most number of clicks and you poke it, you're breaking lots of clicks. So this is an excellent policy. But what is it? What is its disadvantage? Its disadvantage is that it's very expensive, because you now need to find all these clicks and you need to count them. So it's like before you actually find it, it's faster just to run naive algorithm and deduplicate the entire data set. So that would be one example.
Thank you again.